Thank you, Corey. I'm going to talk to you about wide bandgap nanophotonics, and thanks again for hosting and for the tour. So this work actually was performed in Harvard during my postdoc. So that's what I'm going to talk about today. And in the beginning of this year, I moved down to Sydney, Australia. So Sydney is here, and that's like a picture of our campus. The problem is that we are only 30 minutes walk from here. So very hard to motivate students to stay in the lab. But okay. So just give you all working in the same quantum photonics field, so you know why do we do what we do. But just to give you a brief motivation, realistically, we really want to move from electrons to photons. And we want to move our information from one place to another, not via interconnects, not via copper, but using photons. And in a way, we started doing it. So, for example, optical fibers, and indeed, from on the 1 to 100 meters and kilometers of information from house to house or from a factory to a factory, already going via optical fibers. What we want to go is actually inside your electronic chip or inside your chip using photons as means of transportation, and really doing 1 to 50 nanometers, chip to chip. On the nanometers and then micrometer and then centimeter scale, we want to use photons for this. And we are doing pretty well. So, and the reason why we're doing pretty well because we backed from the industry, and IBM and Intel the same. They're trying to make these photonics chips and bring the light onto the nanoscale. And I think this April they released the first prototype, although they didn't actually show any picture. So I had to use their old scheme. Now, that's of course all on silicon. I'm interested more in the wide bandgap materials. And wide bandgap materials allow you to do a bit more science rather than only technology. And my interest is within diamond and silicon carbide and gallium nitride. You have some other wide bandgap materials too. And the reason why these are so interested, well, a few of them. The most important one that most of them have room temperature operation, meaning that if you really want to address a single defect, you don't need to cool it down, all room temperature. The second important thing is it can host defects. So as most of you know, diamond hosts NV, but it has more than 500 optical defects that can be in principle isolated to a single level. And so do silicon carbide, and if you get a nice combination of in-gun quantum dots and gun, you can also work not at room temperature, but very close to. And of course, for communication, they have a very broad bandwidth, and they're all transparent in the visible. So this giving you a very nice motivation why wide bandgap materials is actually very, very interesting. And of course, to do something realistic, we need to integrate them with the photonic structures or to build some sort of element. So we have a cavity and then some sort of photonic qubit and a waveguide. This is not my idea. It's from people before me who proposed and realized it with silicon. And indeed, you have two main building blocks for photonics, photonic crystal cavity and a microdisk cavity. These are basically confine the light, and you can manipulate light onto the nanoscale. So it has some photonic bandgap here, similar to semiconductor bandgap, and you can introduce a defect here, again, similar to a defect into a semiconductor bandgap. In this case, you have a whispering gallery mode, so the light propagates on the periphery. And the most important in this is that you have to have an undercut into your device. This is not possible if you don't have any undercut here. And this is to confine the light in the refractive index change. So that's exactly why most of the work was done on silicon and gallium arsenide, because you can grow them epitaxially, and you can undercut the silicon by, for example, grow it on silicon dioxide. And you can chemically etch silicon, and similar with gas and InGas and AlGas and all these gallium arsenide materials. Now, to know how good your device is, people often refer to the Purcell effect. To the Q over V. Q is basically how good is your light confined. V is your model volume, and you can measure it by photoluminescence or transmission measurement, and that's how you know how good your device is. And I'll give you some numbers in the future. So as I said, optical isolation is really, really important. And of course, what I want to do in particular is extend it to a new range of materials like diamond and gallium nitride. So that's what I'm going to talk about today. I will show you our efforts in fabricating gallium nitride devices, particularly low threshold lasers. And I will show you how we can tune some of these resonators. I will then move to diamond photonics, and then I will tell you a bit about silicon carbide. This is still in process. Okay, so let's start with the gallium nitride. Well, gallium nitride is commercial material. Most of you actually have the device at home. That's your DVD player or other Blu-rays and stuff like this, and they have this blue nice light LED. And it's interesting material because you can do high power electronic, and it has built-in electric fields, which for some applications it's a bad thing, but for some others it's actually a good thing, and I will show you how we actually use this to our advantage. The problem is that it's typically chemically inert. It has a lot of defects. So if you compare it with silicon, it's actually the most defective material that is currently commercialized. There are a lot of defects. Silicon is basically like a vacuum compared to gallium nitride. But nevertheless, the performance is so good that you still can make a properly working device. So what we want to do, we want to fabricate microdisks. We start with a material that has the following structure. It has a sapphire and then a GaN and in-GaN superlattice, which we're going to undercut. And on top, NIN structure. It can be a PIN. And what's different here from other previous works is we're moving towards quantum dots rather than quantum wells. A lot of work has been done over the last 20 years on gallium nitride quantum wells. We want to move to quantum dots because the binding energy is higher and it's potentially good for single photon emitters. Actually, there is now one report on the archive which reported a very nice pillar. And what they did, they took this type of material and just etched it down into a pillar and recorded single photon emission from one of these dots. So how are we going to undercut it? Well, so it turns out that photoelectrochemical etch is a very interesting process. If you put your wafer inside a bath, slightly acidic, maybe 0.04 molar, you can actually shine light. And if your light is higher than the in-GaN energy but lower than the GaN, what will happen is that while you apply a bias, you can actually undercut it. And this is because you will swipe the electron and the holes to the different sizes of the surface, and they will be etched away. And this is, of course, possible because of the inbuilt electric field. And this is the result. So you can have a very nicely undercut microdisk. There are some pillars, but you tune the conditions, and it's actually possible to make a very, very nice microdisk. So we're doing some photoluminescence. So this is with 3 layers of in-GaN quantum dots. And you see the spikes. Every spike corresponds to a whispering gallium mode. There are second order here too. And if you zoom into one of them, you can measure a Q of about 10,000, which is very high. It's the highest basically in gallium nitride resonators. And we believe that the high Q is possible because we actually don't have any quantum wells that contribute to absorption a lot, and they only work with quantum dots. In fact, we need to do some transmission measurements, but in this case it's a bit harder because you need to pull off your transmission fiber down to 500 nanometers, so tricky. So if anybody wants to pull off some fiber, I can send the microdisks actually measure probably a higher Q. That's basically the limit of our spectrometer at this range. So we do some material characterization, and just draw your attention to this part, that once you increase the number of quantum dots from 1 to 3, you actually don't lose your Q, which means that the quantum dots don't even contribute to your absorption limit, which is very, very important for future devices. So your absorption of the quantum dots doesn't limit your Q. So in principle, you can put there even 5 layers if you need. The next thing that you want to do if you have a microdisk already is you want to see if it can actually laze. So here is a nice microdisk with no jagged edges and no pillars hanging off. And if you start pumping it a bit higher with power, so going from 0.15 to 0.6 millijoule to centimeter square, you can actually see one mode dominates, and that's your laser, or potential laser. You don't know it yet. That's just how it looks in real life. This is all room temperature measurements, so no need to cool down. If you plot it on a linear scale and then log, you can actually see clearly the laser transition. This is a very big argument in the literature. Many people plot only this part, but that's actually not sufficient to demonstrate lasing. This only shows you amplified spontaneous emission, which is this peak. So you have to have the second drop here, the second hump, to actually prove that it's lasing. That's the coherent transition, when all your photons are indeed in the same coherent, not state, but coherent one with another. The thresholds are low, not the lowest ones in gallium nitride, but I remind you, this is the first type of devices with quantum dots. And of course, it's still pulsed, but we're now trying to do measurements to make it also laze continuously with continuous excitation. So this is nice, and it's all possible just because you optimize this photoelectrochemical edge and have somehow precise control over the material growth to combine these quantum dots. Now, the next thing you want to do for quantum applications is actually to tune your cavity mode with a single quantum dot emission. So if you remember here, you had the forest of whispering gallery modes. If you optimize your disk undercut, you'll have only a few, but you don't know where the quantum dot emits. So what you really want to do is tune your cavity mode to the single quantum dot, and this is the only way to actually do some Purcell measurements. And if you look at the equation, this parameter here, if you are far away from the resonator, you basically don't see any effect. So that's what we want to do, and people before us tried to do it. There are some methods. Well, you can, of course, deposit the film. That will change your refractive index, and you'll be able to tune. The other way is helium condensation, electric field tuning. Electric field will just tune your quantum dot, of course. It will shift the resonance of the quantum dot. And there's also temperature tuning. Now, the reason why I put them in different colors is because film deposition is, of course, permanent. Once you put the film, you cannot take it down. And these helium condensation and temperature tunings are dynamic. So you do it while you measure and you observe, and once you take it out of the cryostat, it basically disappears. We want to do both of them together. We want to do it both in situ and dynamics and permanent, so that it will be practical for a device application. So the idea here was that if you put it back into the liquid media, into water, for example, and continue irradiate with a 380 nanometer light, you will actually keep undercutting. Well, that's because you have the InGaN superlattice, so you keep undercutting. And hopefully, you will see some change. So this was kind of a Friday night experiment, but it worked. And you can see that in a very, very low power, these are the whispering gallery modes, only 3 here. So they tune. And if you increase the power, they tune even faster. Okay, so you can actually see the change goes from 470 here all the way to 430. So we thought about the mechanism. And the mechanism goes as follows. We put your microdisk in water. We shine laser at 380 nanometers. It will generate electron hole pairs in the InGaN layer. And because of the internal electric field, they will be swiped to the surface. And because we are in water, we somehow etching away the top surface. And because you change the dimensions of your disk, you change the refractive index, and therefore you change the mode position. We repeated this in some non-polar medium, and it didn't work as obvious. But what we really wanted to understand if we etch the top layer rather than anywhere else. So here there was Nan Yu, one of the graduate students, that did somehow clever but very tedious experiment. And what he did is he put a polymer here on the top, just in the middle. And then he did the same experiment. So he irradiated in water for some time, very low power, for a minute. And then he took the polymer away using BOE. And then what you actually see after you do AFM just on the top surface, you see this hump, which means that indeed most of the disk shrank, except off where it was protected by the polymer. And this really proves you that what you actually do is you remove the top layer of the material. And you can run some constant simulations, and they indeed have the same type of shift if you remove 8 nanometers, and it's a very linear process. And we repeated it for several disks, and you can see that its tuning range with time is good. Versus power, it's all linear and predicted, so you can know exactly where to hit your whispering gallery mode and where to stop. Now, how long do you need to shift, or how long do you need to tune? Well, of course, one free spectral range. So if this is the difference between the modes, you want to bring this one to here. And if you keep doing it just by radiating every so often, you actually can tune over the entire spectral range. So that's good, and there is no mode degradation. This is the other very important thing, which is not a trivial thing. So if you start with a Q of about 3,000–4,000, you end up with the same Q at the end. Okay, so that's over 70 nanometers of wavelength. All right, so we'll summarize the gallium nitride part. So we showed that we can fabricate very high quality microdisks, and we can tune effectively the whispering gallery modes, and we can make a laser, which is the basic device. And what the guys are doing now, after I left, now the interesting part's coming up. So you can actually now do Purcell effect, because you can tune your quantum dot to a resonance. And And of course, you can change this top layer instead of having an N being a P, and then you can do a PIN structure and having an electrically excited quantum dot laser. And this is an outstanding goal. And of course, fabricate photonic crystals, which is a bit challenging because of the undercut, but there are students working on it right now. Okay, questions about the gallium nitride part? Okay, so then moving to the diamond. So diamond nanophotonics. So I will talk about the engineering diamond membranes, and I will show you a bit how did we come along with actually making a proper cavity out of it. So diamonds are nice. This is the Argyle pink jubilee. It was found last year in Australia. The biggest, I think, pink was found in recent years. By the way, the origin of the pink is still unknown. So if any one of you want to go to the mining and become a millionaire, if you can answer why diamond is pink. Now, again, diamond is a very interesting material. It has a huge band gap, 5.5. But what's more fascinating is this ability to host all these different impurities. You can dope it with literally anything, and it will change the color. And that's amazing. It's a great tool for photonics because you can choose your wavelength, you can choose the lifetime of your emitter, basically anything. The only thing you need to do is to isolate them on a single level. And many years, the researchers now trying to isolate different emitters and to find which one is the best for your application. One of them is this nitrogen vacancy center, and people are interested in this particular defect because of this ground state splitting that you can optically access and know the spin state, because you can apply this 2.8 gigahertz and drive the spin from here to here, and the decay rate to the 0 state is different from to the 1 state, and you can actually optically detect it. Now, for some time, people thought that this is the only defect, but the more research you do, the more you realize that, of course, there is no unique things in nature. If there is one, there must be another one. And indeed, people now found another one in diamond and another few in silicon carbide. And the reason why people are doing a lot of research into this emitter in particular, because it's your sensor, basically. Magnetic field dependence, meaning that you can sense electric fields, meaning you can sense strain, temperature, etc., etc. So now the key is, if you can control this NV center wherever you want, in a nanostructure inside a photonic crystal, you will have a nice room temperature sensor. The other aspect of this research around the NV is going about its ability to actually have quantum operations. So you can use it as a quantum state where 0 and 1 and actually do quantum computation. So for this, people really want to integrate it into some photonic device to enhance the count rate. And the question is indeed how to integrate. So two very simple approaches is, of course, using geometrical optics. That's something we learned in Optics 101. Do pillars or do a solid immersion lens. And people did it. You don't have any modification of spontaneous emission. Okay, this is just geometrical effects. But in fact, for entanglement, this was enough. So Professor Hansen from Delft actually demonstrated entanglement between two different NVs simply by using a solid immersion lens. And what was prohibiting from this entanglement to happen before is the lack of count rate. Diamond has a very high refractive index, well, not very high, but 2.4, and you just don't collect enough. So with a seal, you enhance your emission by a factor of 10, and you can put two different seals. And remember, it's a solid state system, so you take 10 diamonds, you have a good chance that in 10 different diamonds, the NVs will behave the same, at least on this optical level. And you can demonstrate entanglement. Now, to go one step further, to enhance the emission into the zero phonon line, I will show you in the next slide why you actually need it. You want to modify the lifetime. And most importantly, you want to go to planar devices, because every time you go to companies like IBM and Intel, they will tell you if it's not planar, it's not good. So they care about scalability and planar devices. They don't care how much it costs. They have enough money. But it has to be scalable, and it has to be planar. So there were two very nice parallel works from the group of HP and the group of Professor Lonkar at Harvard. They demonstrated photonic crystals and actually did parcel enhancement. These rings with a waveguide were done by Marco Lonkar. And the Qs are stunning. This is 10 to the 6 in the infrared. In the infrared, that's an important point. Only 10 to the 4 in the visible, where the NV emits. I should have put a diagram here of the spectrum, but I'll show you in the next slide. But still, it's remarkable because people work 20, 30 years in silicon and gallium arsenide to get to these levels. And in diamond, it turns out to be just if you etch it down, you get it. The key is that you cannot undercut. So you automatically induce losses by your substrate. You see this all rests on silicon dioxide. The other crucial thing is you cannot grow diamond on any non-diamond substrate. So you cannot grow diamond on, say, silicon dioxide or other material that you can undercut. So you can only grow diamond on diamond. So there is a great challenge of how do you generate thin membranes to actually make even better devices. So to do this, people in the 90s introduced a very nice method that is widely used in the industry for silicon carbide, actually. And it's called ion implantation. What you can do is you can bombard the diamond surface with a helium ion, for example, generate this amorphous carbon, and amorphous carbon we can etch with any acid. So you implant, you drill 4 holes, you dip it in acid, and you can lift off your membrane. So that's the process. You have a bulk diamond, you anneal, implant, you pattern photolithography, you have this bath with patterned membranes, you're doing some photoelectrochemical etch, all these processes are known. And then you take a pipette and dip and transfer, and you have a nice diamond membrane. Okay? So, I mean, this transfer with a pipette is actually a bit tricky, but, you know, nothing than a few students and a few postdocs can do over a few months of being locked in the lab with no food. No, just kidding. And this is a really 240 micron diamond membrane. And the key is that people realized this membrane is already a few years ago, but when you make a device, nothing was working. So when you actually pattern a photonic crystal out of this or a microdisk, there were literally no modes. And this was surprising because people realized, or people thought, that the damage propagation is only at the end. So when you actually flip it, and people learn now how to flip these membranes, you flip it and you edge this part away, you would have a pristine diamond surface, but that's not the case. And okay, so that's another SEM of this diamond membrane. They can be flattened just by stamping. So going to this, understanding this damage propagation, which we were thought is the first important thing to understand why these membranes are actually not good, we put one membrane with the damage side up and one membrane with the damage side down, and we started thinning them down. So there is membrane A, and we thin it down. And you can see that although you edge the damaged region away, the Raman line doesn't actually become narrower. So the diamond Raman line is a characteristic of how good your material is, and here is it in the blue. Ignore the red and the green. So that's how narrow it should be, but you can see that when you thin it down, it doesn't actually become narrow. So it means that even if you etch away the bad material, you don't actually have a good diamond. When you etch membrane B away, after the first micron, you see that this is already totally amorphous. So not only these diamond membranes are not great for photonics because they are strained, it's also very important to actually know which side you are up, which side you are down. And this is something that people didn't consider before. And these membranes, if you thin down, so this is membrane A, if you actually thin this down, they do fluoresce. But there is no DMR signature. So it means that the strain there is so big that you cannot really detect the spin state of the membrane. So no good for photonics, no good for, not good, full stop. So what can we do? Well, one option is actually use this membrane as a template. And if you take this diamond membrane, only 1.7 micron thick, and you put it in a microwave plasma, and you can regrow completely new layer of diamond. So this is the original membrane. This is the overgrown. You can see this overgrown material. If you grow for a long time, you can actually cover the whole thing. It's one piece of diamond. So it's epitaxial. And then what you do is you drop cast your damaged membrane, you epitaxially regrow, then you flip, and then you pattern your devices and edge the bad material away. Okay, so the process is a bit long, but I can show you that it works. So here it is. On the first generation of devices, you already get Q of about 3000, which is close to what people got from unprocessed, unimplanted membranes. So you just take a bi-commercial 50 micron slab and just thin it down. Okay. So that's good. You can make very nice microdisks. Doesn't require long edge or laser cuts. The other membranes or commercial membranes that you buy, there's a tedious process to actually make those. And you can make photonic crystals. So this is just an example of a photonic crystal, and you can make a nanobeam cavity, and you can have a Qs of about 4000 straight away. So this material is good, and the reason why it all works is because we really get rid of the ion implanted template and we regrew new material altogether. Now, you can also put this on a silicon substrate, and if you put it on a silicon substrate, you can dope your material with silicon. So this was with NV predominantly, as you can see here, only the NV spectrum is here. You can employ it with other emitters. This is the silicon vacancy. As I said, diamond has a whole variety of emitters. This one is particularly interesting for quantum communications rather than computation. What you really need is fast emitters. So the lifetime here is only 1.5 nanoseconds, and it's also ultra bright. And you can filter it efficiently. You see how narrow and bright the zero phonon line is. So you can make a device out of this one, and you can see that you have a mode overlapping exactly with your zero phonon line. Again, the Qs are several thousands in the visible, which is what you get if you work with other material. So that's great achievement. So in terms of the diamond, I showed you that we can now fabricate optically active diamond membranes from this ion damaged material. And people, or many groups in the world, struggle with this idea because for many years you could lift off the diamond membranes, but they couldn't make devices. And it didn't. The knowledge that was missing, that although the simulation shows that all the damage is concentrated only at the depth, that's actually not true. The damage propagates all along, and you really need to regrow new material. The vision from now on, well, of course, on-chip integrated photonics, and we were also thinking about new architectures. And when I say new architectures, I'm thinking, of course, about nature. And if you look at some butterflies, for example, and bugs, they actually have photonic crystals in their wings. Okay, and the way they do it, they just grow it. So if nature can do it, we can do it. And what you can do is you can take one of these membranes, and instead of just growing a fully epitaxial layer, you can grow some pattern and having a photonic crystal made of pillars. So now instead of having a layer, a dielectric layer with holes, you can make a pillar photonic crystal. And that's of course not it, but that's the first attempt of growing just nanodiamonds through a pattern. The other important thing in this way is actually for sensing. Many people want bucket load of nanodiamonds, and they all want them to be the same size with the same properties. Now it's very hard to achieve otherwise, but if you can actually grow it and then flip it and etch it away the original membrane, you can have bucket loads of these nanodiamonds with the same size and the same properties or similar properties. So that's the future, and that's part of the research that I'm going to take back in Australia. Questions? So silicon carbide. So here's a big question mark here, which is intentional. So the silicon carbide was around for quite some time. People, Professor Koito was working on silicon carbide. Nobody really considered it to be any interest for photonics. Many people did MEMS, and there are companies that make millions and billions of just fabricating these gigantic wafers. And if you grow it on a gallium nitride, you can actually have very bright LED. Maybe not here, but you can have very nice LEDs and MEMS devices. So Professor Noda from Kyoto even made some photonic crystals, but really this field of silicon carbide photonics was kind of dead for many years. Until recently, so independently, Baranov and Professor David Avshalom realized that the silicon carbide actually have spin defects, and they can be addressed. So people knew that from calculations back from the 70s that silicon carbide should have spin-dependent defects, but nobody really found them. And then people can actually now address those. You can see it here and here. You can do ODMR or just detect it with other methods. So not only the spin active, they can also be single photon emitters. This work is by Stefania Castelletto, and she showed that some defects, may not necessarily the same ones, but you can produce single defects in silicon carbide. Now this changes the whole story, because now you have another material and you can address your defects individually. It means that it can be a sensor, it can be a qubit, and what's not. So now the question is, again, we're coming back to the same problem, how to make devices without smart cut technique. So smart cut technique is the same, is you implant, you damage, you lift off, and you have a new material. That's how these devices are made. So silicon carbide can recover damage a bit better than diamond, so the devices are working, but we really want to avoid this smart cut technique. We want to make the device without any ion implantation. So what we did is we took an N-type silicon carbide with unintentionally doped epi layer, very thin one, and we know that if we create a photoelectric chemical etch, in a smart way, so slightly different than the gallium nitride, but the principle is the same. You can actually create the electron hole pairs in the surface and the interface here and etch it away. Okay, so you need slightly different lamp with slightly different wavelength and slightly different power, but it works. So this is the etch. The etching processes of silicon carbide are well known. There is no news. You just put a mask and etch it down. But the PEC didn't work quite well at the beginning. So you see there is no undercut, there is just cut. So these are not so good. Back to the lab. The second generation of devices was actually pretty nice. So you can see here this undercut and another disc. We, of course, always start with microdisks just because it's easier to make. And when you measure the Q is straight away 7,000 in the visible. So that's great. So because the material is clean, hasn't undergone any damage, any implantation, you can have very high Qs straight away in the visible. So to conclude, there is a lot of exploring wide bandgap materials. You can choose basically any material, and the bigger the bandgap, the more defects, the more interesting things you can dope it in and do new cool science. And now we're also moving towards hybrid approach in terms of we want to harness not only the mechanical properties, not only the optical properties of each material, but we want to combine the two worlds. And we want to do spin photon, we want to do electro-optics, we want to do different things to combine the best properties of every single material. And innovation takes time, sometimes a century, sometimes a bit faster, but definitely this theme of investigating the fundamental material properties can eventually yield to something very, very nice. So I would like to acknowledge my previous group. So Professor Evelyn Hu, my supervisor. So Andrew Magyar and Jonathan Lee were working with me on the diamond, and David is the new graduate student who will, instead of Jonathan. Alex and Casey and Nan were working with me on the gallium nitride, and me and Andrew did this tetrapod work, basically after work kind of experiment. And it was very, very nice. And I will say that since I moved to Australia, all of you are welcome to visit and spend some time. We have some new toys, not as many as you guys here, but one of the expertise in our university is photoluminescence, so we have quite a few of those, and in situ e-beam chemistry, and I just built a photonics lab. So thank you for your attention.